Hi, I'm Shelley Jones. Welcome to Learning Math with Dr. Jones. Our Facebook group will post a daily math lesson Monday through Thursday at 1 p.m. Eastern Standard Time throughout the month of August. Good afternoon. I'm Dr. Shelley Jones from Central Connecticut State University, and I will be doing a review session for my students in their Math Foundations book, section 3.1, on pages 96 to 98. Okay, the first few examples ask for students to expand the exponential expression into a repeated multiplication. So this is to make sure that they understand how I would expand this power. Okay, so if I have 8 to the negative 2, it means I have 1 over 8 squared, and that's something that we did the other day, which means 1 over 8 times 1 over 8. And we can also actually give the answer to that, which would be 1 over 64. 8 times 8 is 64, although that's not what they're asked to do at this time. So right now we just want to see what is the repeated addition. Okay, question B says a negative 3 to the negative 4 power. Again, we have a negative power, which means 1 over that base to that power, except this negative does not go with the power. The power only goes with what is right in front of it. We would need a parenthesis to make that negative be relevant to the power. So it's a negative 1 over 3 to the 4th, right? So a negative, and then 3 to the negative 4th means 1 over 3 to the 4th, so which is what I have here. And if I want to show this as repeated addition, I would have a negative 1/3 times 1/3 times 1/3 times 1/3. And then, of course, if I were to finish this out, 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81, and I would have a negative 1 over 81. So in this case, my answer would end up being negative. The next one says 3/4, but it's in parentheses, to the negative 3rd power. So that entire 3/4 becomes the denominator, 1 over 3/4 to the 3rd. So 1 over 3/4 cubed, or to the 3rd power. Okay, and so what does that mean? It equals 1 over 3/4 times 3/4 times 3/4. And again, I can go ahead and answer that question as 1 over 3 times 3 times 3 is 27 over, and in fact, I'm gonna do that just because I want to show you something here. So if I have 1 over 27 over 64, 1 divided by 27 over 64 is the same as 1 times the reciprocal. So in this case, I want to simplify this just a little bit to show you that this is equal to 1 times 64 over 27, which would, of course, be 64 over 27. Okay, so in this case, I wanted to do the whole problem out so you can see if I have 1 over this fraction, I want to get rid of that fraction and in the denominator and multiply by the reciprocal. So 1 times the reciprocal of 27 over 64 is 1 times 64 over 27. All right, so this one again, this negative 7 squared means that the squared only goes with the 7. So I have 7 squared is 49, and then I still have that negative there. So that's one of the things we want you to watch is, does that negative go with it or not? Number 8, now this is in a different section. In this section, it says, expand the exponential expression into repeated multiplication and then simplify it. So in this case, if I were to show repeated multiplication, I would have negative 7 times 7. And then to simplify it, I would end up with a negative 49. Okay, So this is expanding it, and then I'm simplifying it. So in this section, section 5 on that page, it actually wants to simplify it. Okay, so here I have a -2 in parentheses to the 5th power. So this time I actually do want 5 of these -2s. 1, 2, 3, 4, 5. The -5 is in parentheses, raised to the 5th power. So I actually want 5 of those. -2 times -2 is +4. So I got a 4 times -2. +4 times -2 is 4 times 2 is 8, so that's a -8. So I'm going to keep track of that. Negative times negative is a +16. And then positive times negative is a -32. So in the end, I have a -32. You can keep track of that if you want. If you wanted to, you could have said a -2 times -2 is 4, +4. Then you have another -2 times -2 is +4. 4 times 4 is 16. That's a +16. And then 16 times -2 is -32. And so you can keep track of it however you want to keep track of it. Okay, the last one. Again, this power, this says 3 times the parentheses 2 to the -5. So the -5 only goes with what's in the parentheses, and that's a 2. So that's 1 over 2 to the 5th. So the 3 I still have, and then 1 over 2 to the 5th. So as you're working through these, you've got to be thinking about those rules for negative exponents. So now that I have this, I have 3 times, and I have 1 over 1, 1/2 times 1/2 times 1/2. I have that lots of times. All right, so this is going to be 3 times 1 over 1, 2, 3, 4, 5. Okay, so 3 times, and since I have 3 times 1, this is like a 3 over 1, I could actually put the 3 in the numerator. So I'm going to end up with a 3 in the numerator, and let's see, 2 to the 5th power, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. So 3 over 32 is what I end up with. So in order to simplify it, although it says expand it first, show that you know what this means, and then come back and do this part, simplify it. All right, so I need to actually multiply out that power of the power of 2. 2 to the 5th power, excuse me. Okay, so then the next section, what is the next section ask us to do? That's question 15. So 15 is still that same section, and it's just saying expand it first and then simplify. So for this 0, this would be, whenever I have a negative exponent, it's 1 over that, right? 1 over that base, 1 over 0 to the 3, and so this is undefined because I cannot have a 0 in my denominator. So I'm just going to leave that one just like that. Can't do anything to it. 2 to the 5th over 2 to the 3rd. I want to make sure you know that that's a power there. So 2, I need 5 of these. I need 5 factors of 2. And then I need 3 factors of 2. And what happens is, because I expanded this, I can see that I have some factors that I can cancel out. In other words, if I write 2 over 2, 2 divided by 2, well, that's 1. And then 1 times anything is itself, so I can cancel that out. Again, I can cancel out that common factor of 2 there, and then I have one more common factor of 2. And so I end up with 2 2's in the numerator, so 2 times 2 is 4, or you could say 2 squared, which is equal to 4. And that makes sense because I had more 2's in the numerator than I did in the denominator. Okay, let's see. Now I have a to the 4th, and then that's raised to the 2nd. So if I were to expand that, I would have a to the fourth times a to the fourth. And if I were to expand that even more, which I'm not going to do here just because I don't have room, but I could actually say a to the fourth means A. I have four of those. A. I have four more of those, right? So a to the fourth squared is a to the 8. Let me just make sure. Squared, I have four of those, and then I have four more, so I have 8 of those. 4 and 4 is 8. Okay. Or 4 times 2 is 8. You can think of it like that as well. R to the 6 over R to the 2. And that's just like I had up here, except here I have variables. So I have 6 of those. 1, 2, 3, 4, 5, 6. And then I have 2 at the bottom. And you know, I asked you to, and actually in the workbook it says, what are some patterns that you see? And as soon as I saw this one, I saw a pattern. I saw this here. I had more in the numerator than I did in the denominator. So in my mind, I'm thinking, I know that my answer is going to end up with more R's in the numerator, right? And how many more? 4 more. Because I had 6 to start with up here and 2 here. So I know I'm going to cancel these 2. And so I have 4 left. So I end up with equals R to the 4th. I could say R to the 4th over 1, but I'm just going to say R to the 4th because that's more simplified. So in this case, the pattern so far that I see, and I wonder if it always works, is if I subtract 6 minus 2, then I know I have 4. I have 4 of those left over. All right, let's do the next one. A times 4, a to the 4th times a to the 5th. So I have the same base, and I ask you to look at when you have the same base and you're multiplying, basically I have 4 of the a's and then 5 more of the a's, so altogether I have 9 of them. And it's true, I didn't write it all out, but I think that you can see from here, when I write it all out, what happens, right? Up here I had 1, 2, 3, 4, and then I had 1, 2, 3, 4, and I had 8 all together. Here I would have 4, and then 5 more, and I had 9 all together. So these were very similar type problems. This was raising a power to a power, so that was 4 times 2 is 8. And this was, when I'm multiplying, I ended up adding those. I didn't add these. 4 plus 2 is 6, so that's not true, right? So I ended up saying whatever this is, if I have a to the 4th and it says square it or it says cube it, it means that I'm going to have a to the 4th that many times. So that many times usually denotes multiplication. So in this case, if I have 4 of these and then 4 more of these, it's times 2. 4 times 2 is 8. Whereas here, I have 4 of these and then 5 more of these. Not 4 times 5. I don't have 20 of them. I only have 9 of them. So if I'm multiplying, so far, it looks like I just add the exponents. So that's one of the things that we ask you to do. What patterns do you see? So hopefully you'll see that that's working every time. And if it works every time, then we can begin to call it a rule. So here, this is very similar, except the pattern I see is that I have more W's in the numerator, in the denominator. So let's see what happens. 1, 2, 3, 4, 5. And then over here I have 1, 2, 3, 4, 5, 6. And I'm going to rewrite this just a little neater. Okay, so I have 5 on the top, 6 on the bottom. The reason I wanted to rewrite that is because we can see here that these W's, these common W's can be canceled out, right? So if I say this W, I take out that common factor of W, I do it again, because W over W is 1, and I can continue to do that for each factor that has the same factor on top as it does on the bottom. The numerator and denominator, I can factor that out. And I end up with a W in the denominator, but nothing in the numerator. And when I say nothing, there's really something there. There's really a 1 there, because 1 times W is W. I can't just leave nothing up there. So I'm going to end up with equals 1 over W. And that makes sense, because I had more W's in the denominator than I did in the numerator. So I wonder if, let's see, we said 6 here. We said 6 minus 2 is 4. So 5 minus 6 is -1. So let's see, W to the -1. Let's just write that. Equals, we're wondering, W to the -1. Let's see, W to the -1, a negative exponent means 1 over that. 1 over W to the 1, which is actually what we have. So far that idea of subtracting the exponents when I have the same base, that seems to work. Okay, so we want to keep thinking about that as well. Okay, 18, I wanted to do this one because, let me give myself a little more room. 18 says t to the 3rd over t to the -4. I wanted to do this one because when you have a negative in the denominator, it's going to end up, if I have 1 over t to the 4 in the denominator, let's just write it. This is equal to t to the 3rd over 1 over t to the 4th. But t to the 3rd divided by this 1 over t to the 4th is the same thing as t to the 3rd times the reciprocal, t to the 4th over 1. Do you see that? So when I flip t to the 4th over 1, 1 over t to the 4th, flip it, take the reciprocal, I get t to the 4th over 1, and I can put a 1 under both of these, and I end up with t, let's see, I have t, I have 3 here, I have 4 here, so t to the 7.
Hi, I'm Dr. Shelley Jones. I'm excited to announce the 1-year anniversary of my best-selling book, Women Who Count, honoring African American women mathematicians. Meet me on Sunday, September 13th at 2 p.m. to celebrate Women Who Count, because representation matters. Stay tuned for a special panel discussion with mathematicians featured in the book, giveaways including a Katherine Johnson t-shirt, and activities from the book. Please register on Eventbrite for Women Who Count's 1-year celebration.